Now observe the buck converter circuit. These are the main components of this buck converter. As I said, this switch can be either a MOSFET or IGBT. This diode provides the alternate path for the flow of current. Inductor is the energy storage device and the capacitor is the output filter. So here when we are analyzing, or when we do the steady state analysis of a buck converter, there are two rules which are to be remembered. One is the inductor volt second is balanced. That is, there is no net change in the inductor current. So average inductor current will be always maintain zero, and your capacitor charge balance, there is no net change in the capacitor voltage. Means capacitor voltage is the average value of capacitor voltage, and inductor current will be zero. These are the two rules we have to keep in our mind when you are analyzing a buck converter circuit. Now we will see the various modes of operation of this buck converter. So let us understand the switch on operation. So switch on operation, when the switch is in on condition. So switch is in on condition means this will act as a closed circuit. So from the time 0 to dt, the switch will be in on condition. We can observe from the switch is in on condition. Then when the switch is in on condition, so the switch is in on condition, this is the positive side of the source and this is the negative side of the source. So the positive side of the source is connected to the side of this diode, and negative side is connected to this side of the diode. So we can see that this diode is reverse biased. So this will act as an open circuit. So during the interval T on, the switch is closed, the source current is flowing through the inductor, then to the load, and then back to the negative side of the battery or the source. So diode is reverse biased, there is no conduction occurs at the diode. So now the inductor voltage, the voltage across the inductor will be, so if we consider VL is the voltage across the inductor, the voltage across the inductor will be Vs minus V0. Vs minus V0. Since Vs is greater than V0, the inductor voltage will be positive. So inductor voltage is Vs minus V0, and since Vs is greater than V0, VL will be positive. So using the inductor equation, di by dt, dIL by dt is equal to Vs minus V0, Vs minus V0 upon L, which is also greater than 0. So the inductor current Vs minus V0 upon L is the rate of change of current through the inductor. So this is also positive. So when this is also positive means the inductor current will be increasing linearly during the T on interval, because this is positive. So when the inductor current is increasing, this inductor will store the energy. Inductor current rises linearly and inductor will store the energy. So this is the condition of inductor current during the turn on interval. Now we will see the second mode of operation, that is when the switch is in the off condition. So when the switch is in the off condition, the source is disconnected from the supply. This entire source will be disconnected from the supply because this is open circuited. However, the inductor current cannot become zero suddenly. Inductor will always oppose the rate of change of current. So even though source is disconnected, inductor current will not become zero immediately. So the inductor tries to maintain the same current direction it reverses its voltage polarity. So voltage polarity will be plus side, plus here and minus. So voltage polarity, because it opposes the rate of change of current. So this will be the it will opposes the voltage polarity, and the direction of current, the inductor will start uh, releasing the energy. So there is a mistake in this. This direction is the correct direction. The inductor current will flow through this direction. So this is the direction of flow of current of inductor. So during the turn off time, or when the switch is in the off condition, source will be disconnected from the inductor, and inductor start releasing energy through the load, and diode will be forward biased, and this is the circuit through which the inductor will release the energy. So now what will happen? The inductor voltage. Inductor is now connected to the load directly. So the inductor voltage will be minus V naught. You see you can observe that the inductor voltage will reverse its polarity. So because of that, the equation will be the inductor voltage VL is equal to minus V naught, and the inductor rate of change of inductor current di by dt is equal to minus V naught upon L, minus V naught upon L. So since it is negative, it is less than 0. So if it is less than 0 means the inductor current will be discharging. So here during the on condition, inductor current will be increasing, but during the turn off condition of the switch, inductor current will be decreasing. Okay, so this is the modes of operation of buck converter. So when you analyze, as I told you, when you analyze this buck converter, always keep one thing in your mind, that the average voltage across the inductor over one complete switching period is 0, and the capacitor charge will also get balanced. Now here, before moving on, there are some assumptions when we are analyzing the buck converter. These are the assumptions. First one is, all these are ideal components. We are considering all these components are ideal without any loss. The capacitor is large enough so that the output voltage is constant. The capacitor and inductor, these are filters. So the capacitor will ensure that the value of capacitor is such that the output voltage is a constant and output current is also a constant value. So this is a step down converter. So input voltage must be greater than the output voltage. V in will be greater than the V out. Here we are considering a resistive load, therefore output current will be equal to V naught upon R, the current flowing through this resistor I naught. I naught is the current flowing through the load resistor. This I naught is equal to, according to Ohm's law, I naught is equal to V naught upon R. Then switching frequency. If Fs indicate the switching frequency, Ts indicate the switching time period. So the reciprocal of your switching frequency will give you the time period, and the duty ratio is T on upon Ts, on time upon total time period, and the range of duty cycle varies from 0 to 1. The value will be in between 0 to 1. So remember these notations: switching frequency Fs, then D is the duty ratio, T on upon Ts, and the duty ratio varies from 0 to 1. So now we will see the mathematical relations. So we have already discussed both modes of operation. So first one is when the switch is in the on condition. So when the switch is in the on condition, so the source, the path of the current is from the source, from then to the switch, then after that the inductor, then through the load and back to the source. So here I have drawn the equivalent circuit of this. The switch is closed, means it will act as a short circuit. This diode will be reverse biased, so that it will not be significant in this circuit. So source is directly connected to the inductor, then to the load and capacitor. So this is the equivalent circuit during the turn on period, that is from the interval 0 to dt. So this is the equivalent circuit. So these are the condition. Switch is in on condition. Diode D is reverse bias. If the diode is D is reverse bias, means ID current will be 0. So during the on condition, the current ID is 0. Source supplies energy to the inductor, capacitor and load. So the source will deliver energy to the inductor, capacitor and load. And we have already discussed inductor current will increase linearly. So this is the charging time. Inductor current will increase linearly and the capacitor charges and maintains output voltage 0. So here VL, the load voltage, sorry, in the inductor voltage across the inductor VL will be equal to V in minus V naught. From the circuit diagram, when you apply this Kirchhoff's voltage law, we can understand that VL is equal to V in minus V naught. You see the polarity. So this is minus plus, this side is plus, this side is minus. So by observing this polarity, we can write this equation VL is equal to Vn minus V naught. And VL is equal to L DIL by dt. VL, inductor voltage, is equal to L, inductance, DIL by dt, which is equal to V in by V naught. So if we rewrite DL as delta IL and dt is the small time, this interval is from 0 to dt. So instead of this dt, we can rewrite it as d duty ratio into total time period. So that is this interval, duration of this interval, and this L is taken to the other side. So we can rewrite this equation as delta IL by dTs is equal to V in minus V naught upon L. So now take this dTs to the other side. So this indicates delta IL is equal to V in minus V naught dTs upon L. So this is one of the main equation that we need to design the components of this buck converter. So along with that, T on time is D into Ts, that we have already seen in the waveform. VSW, voltage across the switch will be 0. Then VD, the switch is short circuited, that's why voltage across the switch is 0. VD is the voltage across the diode. This diode is open circuited, so the voltage across the diode will be equal to the voltage across the source. ISW current, ISW is the current flowing through the switch, and ISW is equal to IL. The same current, ISW, the current flowing through the switch, is equal to the current flowing through the inductor, and ID, current flowing through the diode, will be 0 as it is open circuited. And here DIL by dt is greater than 0, hence your inductor current is linearly increasing. So keep this in your mind. When we are drawing the waveform, we need this for the turn on time. Now we will analyze the turn off time. So during the turn off time, so you can see that switch is in the off condition. So when the switch is in the off condition, so this is the path. Current flow through the inductor, capacitor, resistor and diode. This diode will become forward biased in this interval. Okay, so the voltage VL is this voltage. VL is the voltage. VL is the voltage across this inductor. This voltage is equal to minus V naught. Source is not connected. The source is not having any dependency on the voltage. So this voltage inductor is directly connected to the load. So voltage across this inductor is equal to minus of V naught. So also VL is L di by dt. We can write VL, voltage across the inductor, can be written as L di by dt. So here L di by dt is equal to minus V naught, just rearranging this equation. So like in the previous case, delta IL, DIL can be written as delta IL, which is the ripple in the inductor, which is equal to minus V naught by L, and dt. This interval dt is, this is the turn off interval. So turn off interval is 1 minus d into Ts. So this is the interval at which your switch is in the off condition. dTs is the T on condition. Now 1 minus D into Ts is the turn off condition, time period for the turn off condition. So here the inductor current is negative, so it is showing linearly decreasing. The inductor current will decrease during this interval. And we will see the other parameters as well. T of is 1 minus D into Ts. VSW is the voltage across this switch. The switch is open circuited, so the voltage across this switch is equal to the supply voltage. So Vs is V in or Vs, which is equal to Vs. We can use any notation, Vs or V in. Vd is equal to 0 because now this diode is forward bias, so Vd is equal to 0. So forward bias means this diode will act as a short circuit, so voltage across this will be 0. Then ISW is the current flowing through the switch. So the switch is open circuited, so there is no chance of current flowing through it. So the current through the switch is 0. And ID is the current flowing through the diode. The current flowing through the diode is equal to the current flowing through the inductor. So ID is equal to IL. So these are the value of voltages and currents in turn off interval. So I hope you are clear about the value of voltage and various values of voltage and current during the T on interval and T off interval. So now we will see the duty ratio derivation. This you have already done in the power electronics, which you have learned in the second year. So just for your understanding, I have added this. So inductor current. So we inductor voltage, average voltage assumption we have. There is a rule that average voltage across the inductor is 0. So how we can write the equation for average voltage? Inductor is having two conditions, that is voltage during the on condition and voltage during the off condition. So we can write voltage during the on condition is VL at T on, and VL at T off is the voltage in the turn off condition of the switch. So when you write the average, it is VL T on into T on plus VL at T off condition into T off upon Ts, which is the total time period is equal to 0. So this is the expression for the average voltage across the inductor. Okay, now we have already derived the expression. You can go to the previous slide so that we can see what we have already derived in the mode 1 and mode 2 operation. So during the T on time, voltage across the inductor is V in minus V naught into dTs, plus during the off condition, the voltage across the inductor is minus V naught into 1 minus dTs upon TO. So just substituting the values for these notations in the second step. So this is equating to 0. So this implies V in minus V naught into D plus, so this will be multiplied here. So that's why this is eliminated in this step. Then this is equal to 0. So when you are rearranging this, when you are solving this, you will get V in minus D into V in into D minus V naught is equal to 0. When you are solving this, you will get V naught is equal to D into V. So this is the voltage equation of a buck converter. V naught is equal to D into V in, where D is the duty ratio, T on upon Ts.